lesson. And secondly, let's save the leaks just in case the computer blows up or something. That's no. Linear algebra lecture. Come, it's good. 20 shekel is good. Yeah.
I studied cheaper than that.
You ever been in Thailand? No, 2 shekel, one bucket. The art of negotiating. Okay, so let A be some matrix. The characteristic polynomial. Long word. Oh, A is defined by, call it P of A, X, and it's the determinant of xi minus A. The roots of PA, are called the eigenvalues of A, and more specifically, an eigenvalue is a number lambda in F so that AV is lambda V, where V is a non-zero vector called eigenvector without the pen. Okay. We mentioned lecture number 3. The main subject was the diagonalization of a matrix, finding the eigenvalues and the matrix P and the matrix D, etc., etc. I don't think it's important to this lecture as well, but I don't think we have to mention it right now. I mean, we can probably mention it later on. So right now, I think that's enough. Let's add some properties to the characteristic polynomial. Notice what we mentioned. So yeah, no. Properties of the characteristic polynomial. Okay, so that's a reminder, a little reminder, and I want to show you. I'm discussing with myself about the proof. Should we see it or not? But the properties, let's say it's themselves. I want to write them down of the characteristic polynomials. So one, we can write the characteristic polynomial. No, without the use it. Let's say copy and paste from here. Explicitly. That way, where A is a matrix of n on n. So let's write it down with lambda instead of x, for example. It's lambda to a power of n and some coefficient, call it a n minus 1, lambda to the power of n minus 1, and some coefficient a n minus 2, lambda to the power of n minus 2, etc., etc. Write it down with some visible points, and something like A1 lambda plus A0, where all these A's are in our field. One observation I want to make here is that the coefficient of the greatest power is 1. Because when we multiply all the calculating the determinant, multiply all the elements along the diagonal, it's lambda minus, lambda minus, lambda minus. So we finish with lambda to the power of n without any coefficient, or more specifically, more precisely, the coefficient of lambda n is 1. But the rest of the coefficients can be whatever we want. What I want to say now that one can tell, and yet again, I don't think I want to prove it, just want to write it down. One can tell what the first coefficient, A0, and the last coefficient, A minus 1, can be using the matrix. So now here, these are the properties I wanted to write down. We have, one can call the proposition or something, the properties, whatever. The an minus 1 coefficient is actually the so let's write down in a little example. So we see it. We can have a different color, even something 2-on-2 matrix. Can you see the colors? Yeah. True colors. Some color you like? Teal. Yeah. That sounds great. Let's have a matrix. I don't know. Let's 1, 2, 3, 4, whatever. You should the Hebrew movements, not the English one in the leaks. So if you write down the characteristic polynomial of this matrix A, we have the determinant of lambda I minus A, which is lambda minus 1, minus 2, minus 3, and lambda minus 4. And how do we calculate such determinant? We multiply the elements of the diagonal and the elements that are not on the diagonal. And in conclusion, the characteristic polynomial is lambda squared minus 5 lambda plus 4 minus 6. Yeah, so it is minus 2. We get, yes, n is as the matrix, so it's n on n matrix.
So it's just explaining how each balance is going to be.
Yes, and the one observation we made here is that the coefficient of the greatest power of n is 1. Because we get it from multiplying the elements on a diagonal, which everyone is lambda, 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 lambda. So it's lambda to the power of n without any coefficient. Or yet again, more precisely, with the coefficient 1.
What minus present otherwise you do it either way.
In order to find the eigenvalues, you can. Because a minus lambda I or lambda I minus a is equals 0 is the same. But by definition, the characteristic polynomial is lambda I or xi minus a. So it's lambda minus 1, lambda minus 4, and not 1 minus lambda, 4 minus lambda. Yeah. That's how we define the characteristic polynomial. determinant of when the variable is x, xi minus a. It's lambda, it's lambda I minus a and so on. Huh? Yeah, I mean, when lambda is the letter we usually use here, so I write it down with lambda, but you can write it down with x as well. So what did I want to tell you here on the properties of the characteristic polynomial? I wanted to add two things. I mean, more than just the coefficient of the highest of the greatest power is one. And yet again, I don't think I want to prove these properties, but you can trust me. Trust me, bro. Yeah, they are true. First of all, the coefficient of the lambda to the power of n minus 1 is the negative of the trace of the matrix. Remainder, the trace is the sum of the elements on the diagonal. We can observe that it actually happens in our example, but I want to write down something similar. If you look at the first or last, depending from where you look, coefficient a0, the free coefficient, it is the determinant of a multiplied by minus 1 to the power of n, and again, n is the order of the matrix. We can observe it in our example. In our a color teal. Our example. The characteristic polynomial is lambda squared minus 5 and lambda. So a n minus 1 was actually a1. The coefficient of lambda is minus 5. And the free coefficient a0 is minus 2. Indeed, the trace of a, the sum of the elements on the diagonal, is 1 and 4. It is actually 5. So it's minus ay1, minus a22, minus 1, minus 4. It is minus 5. It is a1. And looking at a0, we can write down the determinant of a, or more precisely, determinant of a multiplied by minus 1 to the power of n. So it is minus 1 to the power of 2, because the order of the matrix is 2 here. And the determinant is 1 multiplied by 4. I can write it down in a long way, so it can be not all together. It's 1, 2, 3, 4. So it is 1 to the power of 1 multiplied by 4 minus 3 multiplied by 2, which is actually minus 2. It is a0. Of course, it is correct, not just in our example. It is universal truth. The coefficient of lambda to the power of n minus 1 is minus of the trace, the negative of the trace, and the free coefficient in the characteristic polynomial a0 is the determinant of a multiplied by minus to the power of the order of the matrix. And yet again, I don't want to prove it. Just take time, just let it know. It's not very important. I'll probably use it later, but it's not very important, so let it be that way. You know what? Let's prove the second one. It is shorter and easier. Won't take so long. Before that, any questions about the properties themselves? Our example in teal. Okay, so let's prove. All right, we'll still teal. Proof. We prove 2. Oh, we prove that a0 is minus 1 to the power of the matrix. So we look at the characteristic polynomial where we plug in 0. On one hand, the characteristic polynomial written down explicitly is this nice, beautiful, long thing. So when we put 0 instead of lambda, all the components are 0. All the components but a 0. On the other hand, if we look at the characteristic polynomial at 0, by its definition, which we mentioned when we started, when we put 0 instead of x, we just get the determinant of fsi 0i minus a. Let's write down with a dot. Looks really without it. And the determinant, skip down so clearly. The determinant of minus a, one of the properties of the determinant we talked about first lecture, the second one, I don't remember exactly where we put every property. The minus is just a scalar multiplying the matrix, so we can take it out, but when we take out a scalar from the determinant, we're giving him the power of the order of the matrix, minus 1 to the power of n. So on one hand, PA at 0 is A0. On the other hand, it's minus 1 to the power of n multiplied by the determinant of A. So we get that they are the same as required. Both of them are the value of PA at 0. Now the proof for one is not very long as well, but it requires to go back to the very definition of determinant using the permutations, which I think we agree we don't want to do now. So we can leave it be. Okay. Any questions about the proof? Okay, we move on. An important notion, considering the eigenvalues, etc., is the multiplicity. I think that's how you say it. Ribui, multiplicity. Yeah, I think it's correct. Of the eigenvalues. So it's a different headline. Multiplicity. It's too much. I think it's correct. Multiplicity of eigenvalue, of n eigenvalue. So let A be a matrix of order n, and let lambda be an eigenvalue of n. We define two important notions about eigenvalue. One is called the algebraic, whatever, multiplicity, and the second one is called the geometric multiplicity. I want to define both of them with the definition and some explanation behind just the definition itself. So can be A or B, one or two, whatever. A, the bold because it's a definition. Algebraic. That's how you write it down, I think it is. The algebraic, sorry, algebraic. Hey, it's algebra. Algebraic multiplicity of lambda is the maximum. Okay, largest, greatest, better, greatest. Okay, such that x minus lambda to the power of k divides the characteristic polynomial. Tachles, we say in Hebrew, which actually in Yiddish. It is actually, write it down with Sevatil, Kolatil. It is actually the power of the, or of x minus lambda in the, or in PA, around the characteristic polynomial. We are given example just now. Let's write down the second definition of the geometric multiplicity. So the geometric multiplicity of lambda is the dimension of, I think I denoted it V of lambda. No, last lecture, maybe E of lambda, where V lambda, write down, we call it eigenspace. What is the eigenspace? The span in the space, the vector space, spanned by the eigenvectors of lambda. What is the geometric multiplicity? Talking tachles. Let's write it down in till.
What do you mean the power of A on the first one, power of x minus lambda?
We'll have an example just now. Okay. You can come. It's okay. It's fun. It's games. You earn big high tech salary later. Huh? Yeah, you eat celery. How do you say celery in English?
Celery.
Yes, celery with C? The vegetable celery. Yes, celery. What is actually the geometric multiplicity? It is actually the number of free variables in the system of equations that gives us the eigenvectors. The AV is lambda V. Can we? Yeah, every lecture should be just till. And what about the test? The final exam. Yeah. Proof by I saw a photo last week. So it's like some Facebook group. It's mathematic memes, whatever. So someone posted a photo from a book. Mathematician can be no. There's some proposition, something like with notations from hell, something very complicated. Stigma of lambda is da. And the proof is just said, you just ask a kid on the street, something like that. So proof by induction, proof by asking kids.
It's like 3 over whatever. No.
Something bad. Okay. Let's have an example. Yes, it's important in order to try to start to grasp the understanding of what we wrote. For example, we look at a We can do it simple. No, let's do it a bit more complicated, not very complicated. Why do we have near for? Yeah, that's enough. I think that's enough. Um, Numbers you all like? Zero. No, we can do one, three. Let's write it down. One, two, three. And for the diversity, 4, 8, 12. First of all, let's find the eigen values. Firstly, we find the eigenvalues using the characteristic polynomial. So, P of A of X or of lambda, whatever, is the determinant xi minus A, which is x minus 1, minus 2, minus 3. If you don't like all the minuses, you can start with a matrix of minus. The example would be the same. And minus 4, minus 8, and x minus 12. We can choose whatever row or column we want. We won't change the uh, length of the solution. So let's open it with the first row, for example. It's x minus 1 multiplied by delete row, delete column. Let's get down so you can all look at it clearly and nicely. Take a photo, take a picture, send it to your parents. Oh, look, Ma, I'm learning math. Some heart, some hearts filter along the way. Minus 2, and determinant. Deleting a column, deleting a row. It is minus 1, minus 3, minus 4, x minus 12. It's not minus 4x, it's minus 4 on one column and x minus 12 on the other. And minus 3 multiplied by the determinant of what is left when we delete a row and a column. It is, if I'm wrong, you're obligated to correct me. X minus 2, minus 4, and minus 8. Minus 8 is always great. Now, what do we have here? X minus 1 multiplied by x minus 2, x minus 12. Is some pale brackets. Write it down more white. Minus 8, minus 3. And minus is plus 2, minus 1 multiplied by x minus 12, minus 4, minus 3, last but not least, minus 1 multiplied by minus 8, minus 4 multiplied by minus 2, and again, too many minuses, the font is too big, the line can't hold it all at one glance. So let's write down the number itself. It is minus 24. It is minus 12. And this is minus 8. I'm missing some x here. It is x minus 2. It is not minus 4. Did I miss some x here as well? No. So that's our determinant. Very nice and very long. We open the brackets. Hopefully we get the root right. X squared minus 14x and t is minus 24 plus 24, excuse me, minus 24 and plus 2 minus x plus 12 minus 12 and minus 3 8 minus plus 4x minus 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 is minus 8. Okay, hopefully I'm not wrong. X minus 1 multiplied by x squared minus 14x. Here we have minus 2x. And here we have minus 12x. Now we can write it down as x minus 1, x minus 14, minus 14x. We can take x out as a common component or something. And x minus 1, x minus 14, minus 14. We have x squared minus 15x minus plus 14 minus 14 and x squared minus 15x. Finally, the characteristic polynomial of A is x squared x minus 15, which can be written down as x minus 0 to the power of 2 multiplied by x minus 15 to the power of 1. So, by our first definition, first of all, the eigenvalues are 0 and 15, the roots of the characteristic polynomial. By our definition, and the tachlis one using the teal color, the algebraic multiplicity of the eigenvalue is the power of its component in the characteristic polynomial. The algebraic multiplicity. Too much fees. Multiplicity of the eigenvalue 0 is 2. And the algebraic multiplicity of the eigenvalue 15 is 1. Now, considering the formal definition, what is the greatest power of x? That, or x minus 0, friendship. That always thank the Hebrew students. The high salary, etc. I call it argazim in Hebrew. That's the slang. I don't know. You can use the exact slang in English.
Stacks.
Stacks. Stacks.
No, that's not that.
Stacks of A.
Like,
Stoinks. I already know all the rappers holding their bills together, the Benjamin Franklin's together. So I was told that maybe the real argazim is the friends we made along the way.
Yeah.
So maybe the real eigenvalues is the friends we made along the way. So, but by our formal definition, what is the greatest power of x minus 0 that divides the characteristic polynomial? When it is written in this way, it's very clear. Look, it's 2. X to the power of 3 won't divide. He's not dividing the characteristic polynomial anymore. And the same for the eigenvalue 15. So these are the algebraic multiplicities of the eigenvalues, one can easily see that the sum of all the algebraic multiplicities is the order of the matrix. Here it is 2 plus 1, which is 3. And we write it down later on a lecture. But right now, just example for the notion itself. The algebraic multiplicity is tachlis, the power of the x minus lambda in the characteristic polynomial. Any questions about the algebraic multiplicity? So the geometric multiplicity considers the question? Right here, I want to refer to lambda as root of the characteristic polynomial. It's like some specific number, while the polynomial itself should be written with the general variable. So I need the two letters. I choose lambda and x. But when it is not needed, this distinction is not needed, we can use just lambda or just x. Okay. So now for the geometric multiplicity, we have to find the eigenvectors. Formally, the dimension of the space spanned by the eigenvectors, which is called the eigenspace. Tachlis, how many free variables there are in the system AV equals lambda V. So for the geometric multiplicities of each eigenvalue, we find the eigenvectors, or we don't have to find them, just to see how many free variables there are in each system of equations. So the general system looks like that. AV is lambda V. In our case, A is the good old 1, 2, 3, etc. matrix. And the V, we can write it with ABC or whatever letters we like. I think we write it down with ABC last week. And lambda is multiplied by ABC as well. We know how to multiply a matrix and a vector. So we have on the left side A plus B plus 2B plus 3C, same. And with 4, 8, and 12. On the other hand, it's just lambda multiplying A and B and C. Why are you here? Should be here. It's 3 equations in our system. What do we have for without the m? Lambda is 0. We have A plus 2B plus 3C is just 0, 0, 0. And they are all actually the same equation. A plus 2B plus 3C is 0. One can write down that A is minus 2B minus 3C. We can write down the eigenvectors specifically, and maybe I'll do it in order to show you the formal definition, the dimension of the space spanned by the eigenvectors. But right now we can say use the tachlis definition. We have two free variables, B and C, or whatever I want. A depends on B and C. We have two, three variables. So the the geometric multiplicity of the eigenvalue 0 is 2, which equals the algebraic multiplicity we'll talk about later. That's always equal, so some greater from the other, etc., etc. Formally, the eigenvectors are A is minus 2B minus 3C, and B at C whatever we want. So the eigenspace space spanned by these eigenvectors, let me write it down clearly. So B and C are from some F. As I mentioned before, our default and our intuition or examples are mostly at R, the field of real numbers. If we want to write it down as a span, we use some shticks from linear algebra 1. We can write down the vector as a sum of two vectors, minus b, b and 0 on one end, and minus 3c, 0 and c on the other hand. We write it down as a sum of vectors. Each letter, each parameter gets its own vector, and we can plug out the parameters. We have minus 2, 1, and 0, and minus 3, 0, and 1. So by the definition of span, the space V lambda is spanned by these two vectors. Every vector in the space is a linear combination of these vectors. There are two vectors in the spanning set. The vectors are not linearly dependent. They are linearly independent. So the dimension is 2. Beam of V lambda is 2. One can write down V0 because lambda is 0 if you want. Not necessary. And as the formal definition states, the geometric multiplicity is the dimension of the eigenspace, which is yet again actually how many free variables you have in the system of the equation A lambda, AV is lambda V. Okay. Any questions? So let's write it down for 0 and you can move on. For 15, that was the second eigenvalue. For lambda is 15, we have this system of equations. How many free variables there are here? So from our first, if we do, let's see, R2 minus R1 or something like that, gives us that 0 is 15a minus 15b or vice versa, it doesn't matter. So a is b. So a is not free, it depends on b. Using the third equation, we get 4a, 15c, rather than the other way around. 15c is 4a plus 8b plus 12c, but a is b, so we have 4b plus 12b plus 12c, not 12, 8. It will be 12 on our next step. 12b plus 12c. This it equals 15c, so 3c, 350, 3c is 12b, which gives us that c is 4b. We have one free variable, it is b. So the geometric multiplicity of the eigenvalue 15 is 1. And more formally, the eigenvectors are A is B, and B is B, of course, and C is 4B. So the eigenspace spanned by the eigenvectors is a space of all the vectors B, 4B, when B is in our field, which is the span of the vector 1, 1, 4, and the dimension of V lambda is indeed 1. This is our definitions of multiplicities, the algebraic one and the geometric one. Okay. Any questions? So we will connect these notions to the concept of diagonalization, but in order to do so, we have to some preliminary, some other things before we get to our main result. We mentioned, but formally, our definition of algebraic multiplicity, that it is the greatest power x minus lambda to the power of k that divides the characteristic polynomial. So I want to talk about division of polynomials more generally. So we can state some statements afterwards and do it correctly. Now, we mentioned the technical process of dividing polynomials by each other in calculus. It was in our second or third lecture. I want to talk right now, I want to talk about more theoretically, more formally, what actually should we expect to get as a result when we divide two polynomials. So I want to write it down that way. The multiplicities of an eigenvalue are important notions connected to the process of diagonalization of a matrix and other subjects. Semicolon. We will observe, watch, see such connections later on. Right now, we have to talk about division of polynomials more precisely, more theoretically, more deeply. Okay? For now, in order to get there, we need to discuss some of the properties of polynomials division. Okay. Nice paragraph as an prologue. Now, write down dividing polynomials with remainder. That's how you write it. Share it. Yes, you can write residue as well. Not residue. No, the word residue as well. A remainder. We learned, or learned if you want, learned how to technically do so. Yes. Theoretically, that's my technically against theoretically to do so in calculus, which very fun, many fun. And we talk about it more theoretically. Now the discussion, as you write it, I think, is more theoretically. Theoretically, that's how you write it down. If not, okay. Feel free to correct my typos. We denote with deg p the degree of the polynomial p. I don't write it in bold font because we already know what is degree, what degree is, but let's write it down again explicitly. What's the degree of the polynomial p? Deg p. Oh, yes. Deg p is the greatest power with a non-zero coefficient. That's all right, I think it is. For example, if p of x is 4x to the power of 3 minus 2x plus 1, then the degree of p is 3. So the coefficient, it's not, if we speak more precisely, it's not all the power. I mean, in Hebrew, you can, there's difference between the power, which is the whole expression, x to the power of 3. It's called chezka. And the basis the ma'arich, the base and the one above. I don't know how to say it exactly in English. So we know that we mean to the number above, not the whole x power of 3, only the 3. The degree of a constant is 0 because it's constant multiplied by x to the power of 0. The degree of a constant polynomial is 0. A nice, you said nice philosophical discussion is about the degree of the 0 polynomial itself. The polynomial that is always 0 It's not important, I think, to our discussion, as far as I can see what I want to tell you here. But formally, one can define the degree of the zero polynomial itself not as zero, but as minus infinity. Why the hell? It's not really important, but just wanted to know. Don't have to write it down, but just wanted to know that the degree of constant is zero. One can argue about the degree of zero itself. Okay. So,
Like no way. No constant polynomial, saying the degree or literally the number zero.
yes, the polynomial, the zero polynomial, which is zero, always zero, whatever you put in.
That kind of makes sense that we might. It's just the way of like something power infinity that's zero, right?
Yeah. You can think of it from many angles. I mean, one can think of a degree. The degree always gets down by one when you derive the polynomial. But when you derive the zero, it doesn't change. It's still zero. So what number we get down by one, subtract one, it's still the same. It's minus infinity. Many other angles to look at it, but it's not very important. Just for you to know. So formally, what do we talk about? We denote, and we know this notation. We denote the set of all polynomials with coefficients from a field F with f of x with square brackets. In linear algebra 1, we mainly discuss polynomials with a certain degree. More precisely, with degree smaller or equals some n. It's a nice vector space. It is finite basis, etc., etc. But I do believe that Erez mentioned the set of all polynomials. It is a vector space above F. It's just not everything is infinite. The base is not finite. It's not finitely generated or something like that. But it's there now just for the set. Now, let some P and Q in our set of polynomials with coefficients from F, such that let's control N. Let's control S, the leaks, such that the degree of P is greater or equals the degree of Q. Now, what do I want to claim here? The technical process of dividing, we know how to do it. I'm claiming something general, something more some theoretical about the result. What do we actually do when we divide polynomials? In that case, so then, or so, whatever, we have polynomials or exist, or there are, so like that, there are some polynomials, let's call them R for the remainder, and PQ, let's write different letter, the G, okay? Polynomials G and R in our set of polynomials such that P is G and Q plus R, where the degree of R is smaller than the degree of Q. Smaller than Q. I mean, if let's say you divide by x to the power of 3, the remainder should be maximum x to the power of 2, not more. Where the degree of Q of R is smaller, much not just equal, it's smaller than the degree of Q, and R is called the remainder, and Q is called the quotient. Yeah? R is called the remainder, stay. Q is called the quotient. That's all right down. If not, you can correct me. I think it is. For example, we can look at an example from calculus. Now, I don't actually remember what was the exact example we did on our second lecture of calculus, which was many years ago, but I think it was still on the board, not on the leaks, so I cannot look in the notes. There are no notes, but I can look at the recording. Yeah, but I didn't write down, so I don't want to exhaust you. It's my fault. I look for the example, didn't we? Where's the calculus playlist? Here it is. That's a blessing, I tell you. All the recordings. I don't have to prepare myself to any class. Just look at the recording of last year, and I do the same. Here in linear algebra, we don't have such, but it's the same. Where is our calculus example? Our calculus example, we got that. Okay, that's an ugly one. For example, there it was part of discussion about finding the partial fractions. So we did the x to the power of 6 on one hand, and as far as I can see, x4 plus x3 minus 2x2 plus 6, x4 plus x3 minus 2x2 plus 6. We did get the following ugly thing, x squared minus x plus 3 plus minus 5x3 plus 6x minus or plus, what is it? It's 18. Of course, I don't remember what I wrote down. Well, I hope it is true. So we can write that x to the power of 6 is x squared minus 6 plus 3 multiplied by this stuff, and we add this stuff as well. If the brackets are not very visible, I can change them to some thicker ones. Here, P is the polynomial we are dividing, which is x to the power of 6, Q is the polynomial we divide by, which is the x to the power of 4, etc., etc. So we got that the quotient, why it is multiplied by Sorry. Q is not the quotient. G is the quotient. I mean, let the Q is quotient. Don't be confused, but G is the quotient. We already have Q and P given to us. Here it is x to the power of 6, and x4, etc., etc. So Gx is the quotient. It's the x squared minus x plus 3. And R, the remainder. One can call it the residue as well. It is minus 5x power 3, etc. And one can observe that the degree of R is smaller than the degree of Q. The degree of the remainder is always should be smaller than the degree of the polynomial we divided by. So first of all, I claim that we know that it is technically working, so it is theoretically working as well, but now I stated formally what we are expecting to get. Polynomial P and Q. P is something multiplied by Q plus another something. The another something called the remainder, and its degree is lesser than the degree of Q. Of the polynomial we divided by. Yeah.
The remainder is how consider a polynomial?
The remainder is?
Consider also a polynomial?
Yes, they're all polynomials here. It can be sometimes a constant one. And when the polynomial P is actually divisible by Q, then the remainder is 0. But there is a remainder still.
Yeah, but no, what I mean is like the remainder here is simply like the power of the values is not whole, right? It's not the whole number, it's not the natural number.
The coefficients need not to be natural number. I agree, but the power of x, which defines the degree, is always a natural number, or 0 when it's constant. Any other questions?
Well, so R is the top part, the denominator of the remainder?
R, when we do the technical process of actually dividing the polynomials, R is what we get in the numerator of the of our new fraction. And again, the degree is always smaller than the degree of the denominator. That was our main step in the process of calculating such integrals, making the degree of the numerator be smaller. So now I'll just state it formally when giving an example. Any other questions? So I want to write down another proposition that we actually all know about polynomials and the polynomials dividing each other. And then we can have our 15 minutes break. We're already on the verge of the break nonetheless. And when we come back on through the break, I'll discuss with myself if I want to prove the second statement or not. Right now, I think not, but let's see. Don't get too excited, just 15 minutes break. Another proposition. Another proposition. Proposition. We all know. Huh? Yeah, love and appreciate and show to our friends when we all gather together. We know is that sum A is a root of P, meaning that P of A is 0, if and only if the corresponding expression x minus A divides P. I mean, if 2 is the root of some polynomial, then x minus 2 divides the polynomial. And of course, vice versa. If x minus 2 is one of the components in the polynomial, then 2 is the root of the polynomial. Huh? No? I mean, I don't think you. I don't even not exactly high school, but yeah, something like that. I mean, if 15 gives us 0 here, then x minus 15 should be one of the components when you write down the polynomial explicitly. Okay. So it's, I don't know if it was stated in this, formulated in these specific words, but it's something that we actually already know. Any other questions? Okay, so let's have a 15 minutes break. Of course, it's 15 minutes, as I like to say, netto. So we resume the recording. The recording is now recording the recording, and we can continue. So now, the statement itself about a being a root of the polynomial p. What the hell? What is this? Okay. And a is root of p if and only if x minus a divides p. We know intuitively that it is true, and right now it is enough for me. I want to use it and the theorem about the remainder in order to prove, as I mentioned, some claims, some statements about the multiplicities of an eigenvalue. As we saw before the break. So I want to write it down that way. Now it can be a theorem if you want. Important. Let A be some matrix of order n, and let some lambda in F be an eigenvalue of A. So for sake of convenience, let's denote we denote the algebraic multiplicity of lambda with I don't know, a lambda because algebraic, okay, and the geometric multiplicity of lambda with g lambda is geometric. Then what is our theorem? First of all, the multiplicities are at least one, and they are at most n, the order of the matrix. And what's most importantly, the geometric multiplicity is always smaller or equals the algebraic multiplicity. In our example, they were both 2 for the eigenvalue 0, and they were both 1 for the eigenvalue 15. Generally speaking, the algebraic of an eigenvalue can be greater than the geometric multiplicity, but not vice versa. This is what I state here. And it's a big theorem. It's a fat one. I mean, there are this inequality and this inequality for both G and A, and the main inequality between G and A. I want to prove that they are both, I don't want this second. I want to prove that they are both greater than 1 and both are less than n. And about the main inequality in the middle, let's first write down the proofs for the other one, and then we'll discuss the connection between them. Okay? So, proof of the bigger P. Okay. So, first of all, let's look at the geometric multiplicity. For GA, what is actually GA? Yes, GA, we know that, with K, that GA is the dimension of V lambda. Now, generally speaking, a vector space can be the zero space, so its dimension can be zero. But why, when we speak about dimension of eigenspace V lambda, it is always greater than zero? It is at least one, because V lambda is the space of solutions of the system AV lambda V that we call the eigenvectors. We can think of it as the space of solutions of the system. We're moving lambda V to the second side, and we put V out. We already did it. Or A to the other side, it's the same. We already did it in our last lectures. Lambda I minus A multiplied by V is 0. And we have special notation for such spaces. The spaces of all the vectors that multiplied by a matrix gives us 0. We called it the null space. We denoted with n. I guess you saw it in your last course. So we can say that V lambda is the null space of the matrix lambda A I minus A. Too many right brackets. And so the what is it? So the GA, which is the dimension of V, is actually the dimension of this space. Yes, so now for variables, but right now I just want to claim that it is greater than 0, which is 1 or more. And why is that? We know that by definition of definition, there exists some V, non-zero V, such that AV is lambda V, meaning that V is in the null space of lambda I minus A. And finally, because there is a non-zero vector in the space, the dimension of the space is at least 1. The space has a non-zero vector in it, so its dimension is at least 1. On the other hand, the vectors here are all taken from f to the power of n, vectors with n entries. The null space of lambda I minus A is contained. It's actually a subspace, so we can write it with the sharp notation, not the circle one, of Fn. So the GA, the dimension of it, let's write down 2 steps. First, the dimension of n of lambda I minus A is smaller than the dimension of Fn, which is the GA on one side and N on the other side. So the geometric multiplicity is between 1 and N, as I claimed. Any question about that proof? Okay. What about the algebraic multiplicity? Now we use the propositions of polynomial division we mentioned earlier, or write down in a different. Now, for A lambda, by definition, it is the greatest k such that x means lambda divides, the power of k, of course, divides the characteristic polynomial. On one hand, again, the degree of the characteristic polynomial itself is n, the order of the matrix, as we have mentioned when we started our lesson. It is lambda to the power of n. So the polynomial x minus lambda to the power of k, which divides PA, has a degree of, at max, n. I write it down a bit differently. On one hand, we have also on one hand the division itself gives us that the degree of x minus lambda is smaller or equals the degree of PA. Now, degree of PA and N and degree of x minus lambda K is A lambda. So we have that A lambda is smaller than N. On the other hand, we know that lambda is a root of PA. So by last proposition we wrote down before we got out to a break, x minus lambda, and that's it without any power, divides the characteristic polynomial PA. If x minus lambda, which is x minus lambda to the power of 1, of course, divides PA, the greatest K that satisfies that is at least 1, because 1 to satisfy the division. We get for A lambda, not GA, just it's not GA, it's G lambda. Why did I start with GA? Because we came back from the break. I was confused. It's G lambda and A lambda. That's how I call them. And here it is A lambda, everything is good. Any questions? Now, for the main inequality states that for every eigenvalue in every matrix, the geometric multiplicity is not larger, not greater than the algebraic multiplicity. It's not very, very complicated proof on one hand, but it does require some of the notions, not so basic notions from the first course, like multiplying column by column or something like that. Our time is short, our syllabus is long, so I want to move on. But of course, it is correct, and we can use it how much as we want. Okay, so I move on. At some point, as I already mentioned, I want to state some statements about the ability to diagonalize a matrix using the multiplicities we are learning about now. In our last lecture, we talked about the diagonalization, why it is important, why is it necessary, why it is common. And we mentioned that a matrix is diagonalizable if and only if one can find, can build, can generate whatever a basis to Fn based on only eigenvectors of A. Now, finding all the eigenvectors and looking is it a basis or not may be exhausting and complicated. So we want to achieve some statements, claims, whatever, talking about diagonalization using multiplicities, the multiplicities of the eigenvectors. So I will take values can give you some spoilers if you want. Different color. We chose teal today. So spoiler. Matrix A is diagonalizable. That's how you write it. Now let's say, listen. Diagonalizable. Let's put A. Diagonalizable. If and only if for every eigenvalue lambda, the algebraic multiplicity and the geometric multiplicity are the same. And this is true if and only if the sum of all geometric multiplicities is n, where n is the order of the matrix. You can edit here. So instead of the basis containing only eigenvectors, this simple criterion because it's two of them, to check if a matrix is diagonalizable. If for every eigenvalue, the multiplicities are the same or it is equivalent, the sum of all geometric multiplicities is the order of the matrix. So we want to get there. Want to get you there. But we have to walk through not very long, but not short as well, way before we get there. I don't want to promise that we will see it today, but I'm not promising we'll see it next week. Let's move on and see how it goes. Yet again, I remind you, I'm trying to follow these notes from the drive. They're in Hebrew. And, they are handwritten and not computer written, but they are good nonetheless. Okay, so this is our main goal, the spoiler here. Let's go to it. No, I'm not sure again that we'll finish it all today, but we always have the next lecture until it's the last lecture itself. Okay. So I first claim a proposition. Proposition. Eigenvectors. Sorry. Eigenvectors of different eigenvalues are linearly, let's write it down, independent. Let's write it down, independent. You understand what I want to say. Did Nir do it in the practice or put it in homework? This claim? Eigenvectors of different eigenvalues. And the last what? Homework or practice? Practice. Okay, so proof. Proof. We saw it with Nir. Okay. You want to write it down real quick? Okay, let's write it down real quick. Okay. And we can have a different color or teal color. CO teal colors. Cyan, yes. There's a video of some, mobile game. You have to say the words are coming at you, names of colors, but every word is in a different color of the. So it's written in green, but in blue. Okay? So in order to pass the game, you have to say the actual color of the word or the color that the word says, and vice versa, whatever. So this is a video of someone who gets it is orange, but it says cyan, or it says cyan, cyan, cyan. It doesn't work. And he's like cyan, and then the words goes. I mean, it succeeded. It goes on. What? That's how you say it. The cyan. Don't know how you actually say it. I say cyan. How do you cyan? How do you pronounce it? Cyan. So let's prove it just quickly for those who weren't in the practice or something. Let's whatever lambda and mu be different eigenvalues, and let v be an eigenvector of lambda, and u be an eigenvector of mu. We want to show that they are linearly independent. Why is it taboo? Linearly independent. Meaning that there is no such A that V is a U or something like that. We can how do you say it in English? נניח בשלילה. Negative please? Assume a contradiction? Yes? Okay. In Hebrew it's להניח על ידי סתירה. מעניין. Assume by contradiction that they are dependent. There are some A and B in F such that AU plus BV is 0, and A and B, one can be 0, but the other one cannot. I mean, some of them, or the two of them, are not 0. How do I write it? A is not 0, or B is not 0. This is the definition of linear dependency. There is a linear combination with coefficients not all 0 that is 0 itself. So why is it not true? Why it is a contradiction? We can multiply it by A and multiply it by A. We can use the very definition of eigenvalues and eigenvectors. Let's write it down. Multiplying, that's right, by A gives us AAU plus BAV is 0. Now, AU is mu U, and BAV is B lambda V, right? That's how we, I mean, multiplication of matrices is not, we know that, is not commutative. You cannot change the order of the components, but it is distributive. It's called pilug in Hebrew. You can put the scalars away and the sum away and get, what did we get here? Now, the question is, how do we, and if it wasn't practice, you can help me. How do we continue from here? How can we show that we have a contradiction? Now we know that lambda and mu are different numbers. Okay? Any idea?
Say you have A and U, U and B that are different vectors in the vector space of each of them, right?
Yeah.
And multiplied by the so you said we say that AU and AB equals gamma gamma U and gamma B, right?
Yes. No. No, no.
Sorry, mu U and mu B. But they have to be the same so for it to be zero, right?
What?
For them to be equal, the difference should be zero.
Yeah, we can go through that way. Now we know that AU and VV is 0, right? We know that. So we can write down that, oh, I want it to go from here like that. Now they do it. Well, see, we've been in black, so I'll till it later. Now we know that AU is minus BV. So we have 0 is mu multiplied by minus BV plus lambda BV. And we can take our BV outside. And it is multiplied by mu minus lambda. Or lambda minus mu, if you want to be more precise. It doesn't really matter because it is 0 nonetheless, but whatever. Now, V is not 0 because it is an eigenvector. So we have B is 0 or lambda minus u is 0. But both lead to a contradiction if lambda minus u is 0, then lambda and bu are the same eigenvalue and not different one. If b is 0, we have, remember that AU is minus BV. So we have AU is 0, and then U is 0, but then we know that U is not 0. It is an eigenvalue vector again, and A is not 0. Because if B is 0, A might be a non-zero scalar. So we have a linear dependency by definition. I'll till it as well. And yet again, as you said, it was in the practice, so don't know why, in hindsight, why did I actually did prove it here? But whatever. Not so bad. Any questions about the proof?
For every different eigenvalue or some intersection, you have
Only zero. Zero is not an eigenvector by definition, so none.
what are we trying to prove exactly? Because
Talking about the vectors, eigenvectors of different eigenvalues are linearly independent. Talking about the eigenspaces these vectors create, eigenspaces of different eigenvalues, the only intersection is zero. Now I can say it. I mean, first of all, the question, which, as I believe, appeared in the with near, it's simple. Take two eigenvalues, two corresponding eigenvectors. They are linearly independent. But now we can say it. We call it corollary, right? The corollary, fancy word for maskana in mathematical English. Corollary. Let A in F and N, and let's call them lambda 1 to lambda k. It's a different letter. It's not lambda n, because we know that some of the eigenvalues can appear more than once. So there are k different eigenvalues. Let bi be a basis for the eigenspace v of lambda I. Again, the eigenspace is the vector space spanned by the eigenvectors of lambda, and basis for the eigenspace vi.
in lambda one, lambda yeah,
Eigenvalues. Each eigenvalue has, first of all, an infinite number of eigenvectors. And talking about dimensions, the space spanned by the eigenvectors of each eigenvalue, which we call the eigenspace, can be of dimension greater than 1. We had an example before the break of eigenvalue. It was 0, as I remember. With the geometric multiplicity, the number of eigenvectors in the basis, the dimension of the eigenspace, 2. Yeah. So every eigenvalue has its own eigenspace containing its eigenvectors and 0 for it to be a space. And I denote let bi some basis of every eigenspace. B1 space of basis of the first v lambda 1 eigenspace, etc., etc. By our last proposition, on one hand, vectors in the same basis are linearly independent because it is a basis. On the other hand, vectors from different bases, one from the basis of v lambda 1, the other from the basis of v lambda 2, or whatever, are linearly independent as well because of our last proposition. So one can write that the set, then, it's the conclusion, then the set B1, how do you say yichud? Unity? Unity. Yeah. Unity. Union. Yeah. Ichud, not yichud. It's with aleph, not with y. Yes. Yeah. It is no, it's not the same origin. It's not the same origin. Then the set is linearly or linearly. You had I here or not? can tell me afterwards. Independent. Let's write it down as an explanation. We can write it down explicitly as some long linear combination of every vector in B1, every vector in B2, etc., etc. I don't want it. It's just hard work, not necessary. We can explain as I already explained. If can the vectors in every BI are linearly independent because it's a basis, it's by definition. The vectors from different BI's bases are linearly independent because of our last proposition. But if you take eigenvectors of different eigenvalues, they are linearly independent. Any questions about a corollary? Okay, so now we can move to the first equivalent condition for diagonalizable matrix, that the sum of all the geometric multiplicities is n. So this can be a theorem or a statement or whatever. Let A be a matrix in Fn on n. In lecture number 3, we know, by the, it's not a theorem, right? So right away, by definition, A is diagonalizable if there are D, a diagonal matrix D, and invertible. What? No, because we are talking about matrices of finite order, of order n. So there are at most n different eigenvalues. So there are at most n different linearly independent eigenvectors. So you cannot have infinite number of linearly independent eigenvectors. Yes, but when we looking at the number of eigenvectors, each eigenvalue has its own eigenspace. The number of eigenspaces is finite. Every such space has an infinite number of bases, probably. But what I say is that if we take for every such eigenspace, which are k, nothing more, for every such eigenspace, we take some basis bi, the union of these b's is also linearly independent.
And the one going to be an amount of B for it.
The amount of B's is, if I want, maybe that's what confused you, because it's not N, it's K. It's the, for every eigenvalue lambda, there is an eigenspace V lambda, which have a basis Bi. Now, it has many different bases, of course, but it's not what I say. I say that if you take one specific base for every eigenspace, and you look at the union of all the bases, you will have a linearly independent set. Maybe on the first look, but now that we know that in every Bi, inside Bi, the vector is linearly independent because it's a basis. And if you take vectors from different Bi, from B1 and B2, etc., it is linearly independent because of our last proposition that you already saw with near, and we proved it here as well. So it's linearly independent, generally speaking. You take vectors from the same Bi, from different Bi, it's all the same, it's linearly independent. Now, formally, we should write some, B1 is the vectors V11 to V1T, and B2 is V21 to whatever, and write long, nice, thick equation. The combination is 0, and proving that all the coefficients are 0 as well, by definition of linear independency. But the explanation speaks for itself. It's just a long, tiresome writing. What?
Geometrically.
Yeah.
The eigenspace might be a line.
No. I mean, for example, you can look at our example here. The eigenspace is spanned by two vectors, which is a plane in the space of R3.
Right.
And talking about higher dimensions, we cannot imagine the concept. So what was I saying? A is accessible if there are a diagonal matrix D and an invertible matrix and an invertible matrix P such that A is PD P minus 1, and we showed why it is important in lecture number 3, because we can now calculate high powers of the matrix, and this is important because talked about video games or whatever. We already said we have already said it was in the past perfect, whatever. So the present perfect, we've already said that A is diagonalizable if and only if there is a basis of Fn containing only eigenvectors of A. In other words, we can build, manufacture a basis for Fn using only eigenvectors. That was our last theorem, our last claim in lecture number 3, as far as I can remember. Now, our theorem is that A is diagonalizable if and only if the sum of the geometric multiplicities is in the order of A. And our second equivalent condition to A being diagonalizable is that for every eigenvalue, the algebraic multiplicity and the geometric multiplicity are the same. But as far as I can see, the clock on one hand and the students on the other hand, what we write down in the theorem here is enough. I want to explain it. I can shove out the proof here, I think. And next week, after a good reminder, we'll talk about the second equivalent condition. So let's explain why is it so. Proof. On one hand, if the sum of the geometric multiplicities is n, if the sum of the geometric multiplicities is n, by our last corollary, we know that the union of the bases of the eigenspaces is a linearly independent set. We can use the same notation we used in the corollary for that, for example. G of lambda I, G lambda I is the dimension of V lambda I, the eigenspace, which is the number of elements in Bi. So if we want to calculate the dimension of the union of the bases, it is the sum of the dimensions because they are all linearly independent, don't have any common elements. Every one of them is dim of Vi, or just the big of Vi. No, the dim of the space they are. I forgot the span here. Space they are spanning. Dimension of the space they are spanning is the sum of the dimensions that each B is spanning, which by definition is the to its n is the eigenspace, because they are bases of the eigenspace, and it is the dimensions of V lambda 1, V lambda 2, etc., etc. to V lambda k. And this is the sum of the G, which in this direction of the proof, we know that it is n. So, what do we have here? A linearly independent set with a spanning dimension as same as the space itself. I don't know how errors call it in English last semester, but we have a theorem. In Hebrew, I call it השלישי חינם. The third one is free.
That's one.
2 plus 1. Okay, it's a good name. 2 out of 3 conditions, out of 3 following conditions, always gives us the third one. If a set is linearly independent, if a set is spanning the space, and if a set has the number of elements as the dimension of the space. Now, the set is linearly independent by our last corollary, and the dimension of the space spanned by the set is actually the dimension of the space itself by our assumption here in this direction of the proof. So it is a basis, very exciting, I do agree. So is a basis of Fn, which means that A is diagonalizable by our theorem from lecture number 3. Right here, no. But if you generally take two bases of two subspaces, the bay when you take the union, the set you get can be linearly dependent. Right here, no. By definition, a basis is linearly independent spanning set.
So like the idea of one, like kind of.
No, it's very sometimes very useful.
No, it's useful, but it's like kind of like it doesn't work for one way. Like if we know it's a basis, then we know that the other two is true.
No. But the 2 plus 1 here says that if you have
it's linearly independent, spanning, and the dimension is n.
Yeah.
So not basis.
A basis that it's a spanning linear independent. So if you have a basis that is true because you have
a basis is already two of them, yeah.
Wait, say the two all again. Linearly independent,
spanning, and the dimension is n. Dimension is the number of elements in the group, in the set. Okay, we're already finished. Any other questions?
I feel like I have to go over this again.
Okay. Then you should. You should
Yeah,
trust yourself, trust your feelings.
Yeah, no, it's just like we could get to the sum of the G gamma. It's like, how did we get here again? Sure.
Yeah, we walked through some lectures. Notice that we only proved one direction of the theorem. The other one is we assume that A is diagonalizable, and we prove that the sum of all the geometric multiplicities is n. We're not going to do it now, of course, and I think we'll pass over it, next lecture either. So after a reminder, next week, just all be healthy and well. We'll continue from here to the second condition equivalent to diagonalization. Okay. Yeah, bye.